the speakers for the? Are there two of you?
So yeah, he's right here.
Okay.
I'm going to start us off.
Okay, sounds good. Okay, so for the last talk of this session, hopefully we'll have the slides up soon, but for the last talk of the session, Yuanjie Ren and Kevin Smith are going to tell us about efficient preparation of solvable anyons with adaptive quantum circuits and constant depth preparation of matrix product states with adaptive quantum circuits. And I think Kevin is going to start us off.
Yeah, sure. Great. So, right, this is going to be a sort of a pair of more rapid-fire talks here. I'm going to start us off talking about my own work on matrix product states and preparing these with dynamic circuits. And then I'll hand it off to Yuanjie in about 10 minutes to talk about his work. So when I say the words quantum circuit, probably the picture that many of you have in mind is something like what's on the left-hand side here, where we're applying some sequence of single and 2-qubit gates and making measurements at the end. So really the bread and butter here is the local unitary gate. However, when we think about today's hardware, we really have access to a broader set of resources. So we have things like mid-circuit measurements, classical computation, and even feed-forward operations, where we're taking the results of our measurements and feeding it into the logic of what unitaries to apply next. Okay, and so you take this broader toolbox all together, and this allows you to form what are called dynamic or adaptive quantum circuits. These are words that I'm going to be more or less using interchangeably throughout this talk. And so at a high level, what the theme of both of these talks today is going to be is the following question. Can we actually leverage this broader toolbox to perform certain tasks more efficiently than we could otherwise by just relying on local unitary gates alone? Okay, and so in this first part, I'm going to tell you about my work on preparing matrix product states. And what I'll show you is that on the one hand, what's quite well known is that any matrix product state you can prepare with a linear depth circuit composed just of local unitary gates. Okay, so that's in unitary land. But what I'll show you is that for certain matrix product states with particular properties, we can drastically speed this up and prepare them in constant depth with dynamic circuits. And this is something that for many of these states is provably impossible with local unitary gates alone. Okay, so time is short, so I'm going to make this pretty quick and just sort of dive into how this works. So it's okay if you don't know exactly what a matrix product state is for the purpose of this talk. It's just this diagram here, okay? So each of these red circles, these indices pointing up, these are my physical degrees of freedom in my state. And underlying this are this sort of a series of tensors which are all contracted together along this virtual dimension with the size given by what's known as the bond dimension, which sort of tells you how entangled the state is. Okay, so this is a matrix product state and the thing we're going to try to prepare. And in order to explain how the preparation protocol works, it's going to be helpful to sort of root it in a particular example. So I'm going to give you the example where we first discovered this trick and then later generalized it. So this is what's known as the AKLT state. It's a super historically important example of a matrix product state. It's also a prototypical example of what's called symmetry-protected topological order, and this is going to become quite important for its preparation, as you'll see. And the thing that I want to highlight here is that the AKLT state, it has a non-zero correlation length. And so what this means is it's actually impossible to write down a constant depth unitary circuit with just local gates to prepare this state. And even if you just want to prepare it approximately, not exactly, sort of relax this, you still need at minimum a log depth quantum circuit to prepare it approximately. This was a result shown just last year. What I'll show you, though, is that you can evade these no-go theorems by turning to these, this sort of broader class of circuits, adaptive circuits. OK, so how does this work? I'm just going to sort of lay out the 3 different ingredients and then put them all together at the end. So the first, the idea is super, super simple. So the first is we're just basically going to prepare small copies of our matrix product state. Okay, and so this is what's shown on the right-hand side here. The details of how this works isn't so important, but at a high level, we initially prepare some Bell state up here. And then this Bell state, this Bell pair, we then sort of use it as kind of like the seeds to grow the state, okay, as shown on the right-hand side. And an important feature about the small versions of the matrix product states we prepare is that they have these sort of dangling bond qubits, which sort of elevate the virtual space to an actual degree of freedom on the hardware. Okay, so that's the first step. The second ingredient is that then once we have multiple copies of these small states, we can actually glue them together with measurements. And the way this works is you make an entangling measurement on these dangling bond qubits. For the AKLT state, we're going to want to do this by measuring in the Bell basis. And when you make that measurement, the state that comes out of this is the following. So we have some random Bell pair sitting up top, right? This is just whatever Bell state we've projected into. We know the result. And then paired with this is something that looks like a longer version of the state we're trying to prepare, up to the feature that it has this defect B sitting in the middle. And that defect, it comes from the random outcome of this Bell measurement. But the important thing is we know exactly which outcome we have. And you can show that this defect, because we're measuring in the Bell basis, in this case, it's one of the 4 Pauli operators. Then the third ingredient is that we can actually then correct these defects. So for the AKLT state, the way that this works, just give a little more detail, is that it's, as I mentioned, an example of symmetry-protected topological order, in particular protected by Z2 cross Z2 symmetry. And how that symmetry manifests at the level of the tensors which build up the state is through this relationship on the right-hand side in this dashed box. Okay, and so it basically says that if I take my local tensor and I conjugate it by any Pauli operator on this virtual level, then there's some equivalent unitary that I can do on the physical degree of freedom that carries out the same action. And so at a high level, what this means is I can use these symmetry operations on my physical degrees of freedom to manipulate these Pauli operators on the virtual level. Okay, and so this is how this works. We know what defect is sitting here. We can then apply UB to essentially slide it over one, apply it again to slide it over further, and finally remove it at the edge. Okay, and I sort of walked through this sequentially just to sort of illustrate the point. But of course, all of those operations all commute with each other, so we can apply them all in a single layer. Okay, so we can now put all of this together. I think you probably get the idea already. We're just going to prepare lots of small versions of our state. We can then sort of glue them together with these fusion measurements. And then with some classical computation, we can then use feed-forward operations under particular circumstances, which I'll get to in a second, to correct these defects. Okay, and this is the high-level idea. And the point is now this is a constant depth, extremely simple way to prepare instances, this class of states, and it requires only a linear number of ancillas. Okay, so what states can we actually prepare with this strategy? I don't want you to walk away thinking you can prepare any matrix product state in this way. Okay, and at a high level, the thing we had to solve to answer this question is we need to be able to correct these defects. So we need to understand when we can push around these defects on the virtual level through these operator pushing relationships shown at the top. And so the challenge is you need to find a complete sort of set of these pushing relations that form a complete measurement basis of dimension d squared matrices, where d here is the bond dimension that's pushable. Okay, so I don't have time to get into the details of sort of all of the cases where this is possible. That's what the paper is about, so I recommend taking a look if you're interested. But I'll just sort of highlight what I think is the most interesting scenario, which is sort of the generalization of the AKLT state example that I just showed. So the special scenario is when you have on-site symmetry, this guarantees the existence of these pushing relations. So down here, this is essentially the generalization of this AKLT state pushing relation I just showed, where these VGs, they form some representation now of your symmetry group G. And the sort of technical result we proved was that if these VGs form an irreducible representation of your symmetry group, then those states you can prepare in constant depth. So this is quite a technical result, but just at a high level, the key takeaway I want to give is that there's this very close relationship between the symmetries of the state and the basis that you measure in. Okay, so what states can we actually get out of this? So we show in the paper how to prepare both normal and what are called non-normal matrix product states, where the former correspond to short-range entangled states, such as the AKLT state, and describe symmetry-protected topological phases of matter. And the upshot here is that unitarily, the best we can do to prepare these states with just local unitaries is a log depth circuit. And here we're showing that under certain circumstances, when you have these pushing relations, you can now speed this up to constant depth. And non-normal matrix product states describe states such as long-range entangled states, like the GHC state, symmetry-broken phases of matter. And here the upshot's even greater in that you require at minimum a linear depth circuit unitarily. Okay. And we give a lot of different examples in the paper, so I recommend just go taking a look or talking to me if you're interested, but just to sort of flash a few. So any state with zero correlation length you can prepare in this way, so any fixed points of any quantum phase you can get. Maybe one of my favorite examples is, I think the new thing here is we can also prepare states with non-zero correlation length and constant depth. And I think a nice simple demonstration of this is this Z2 symmetric family of matrix product states that actually interpolate between the cluster state and the GHZ state. We can also prepare everything in between. And we give lots of examples of families of matrix product states with finite abelian, non-abelian, and even continuous symmetries, where the latter have been shown to be useful for measurement-based quantum computation with qubits. And we also discussed the idea of sampling random matrix product states in constant depth. You can do this as well, or sample from particular symmetry-protected topological phases. OK. And with that, yeah, thank you for listening, and let me hand it off to Yuanjie.
Okay, so I'll talk about some adaptive circuit preparation for 2D topological orders. Hope you've enjoyed the first part. The second part is very related. And the work is done with Dom and Nat. So here's the plan. And there are a couple of motivations here. So the first motivation is that different long-range entanglement in topological orders can be classified using the equivalence class of finite depth local unitary. That's a canonical way that has been invented like 15 years ago. However, in the quantum computation process, this can be more natural where we have measurement. So instead of considering just finite depth local unitary, we should also add adaptivity, and that was already talked about. So we'll use adaptive finite depth local unitary as the equivalent class to classify quantum phases. And for example, the product state, ground state of the quantum double of Z2, which is the same as toric code, and double of D4 and double S3 can all be seen in the same trivial class because the second classification is more coarse-grained. You are allowed to do more things. However, the Fibonacci topological order is of a different class. And you can also view this as an effort to do quantum simulation of topological orders and also TQFTs. So such a system can be also used to encode logical information as the topological quantum code. So the advantage for this work is that the constant depth circuit with respect to the anyon separation, no matter how far they're separated, you can always do it in constant depth. Previously, people thought that this should be done in linear depth. And the Krams-Wanier, if you just use unitary, it's also linear, but use adaptive unitary, it's constant depth. And hopefully, my talk and Kevin talk makes you believe that adaptivity will make the quantum circuit, which is just unitary, more powerful. It's given fast classical feed-forward, and in this work, we want to explore the limit of this adaptive circuit in 2D. And so here's the main result. A solvable Anyons theory is a topological order that can be obtained by a series of abelian gauging. You'll see such hierarchical structures very often in this work. And we show that for such solvable theories, you can prepare not just the ground state, but also long Anyon string operated in constant depth. It goes beyond just solvable groups, which were the previous result. And there are a couple of examples, for example, double Ising topological order, quantum double S3, and also Tambara-Yamagami category for abelian groups, and so on. So let's go with the simplest example to illustrate. And instead of using 0 and 1, I will also be using mass both 1 and psi corresponding to the trivial and also the non-trivial simple objects in the Ising category. This is just to make the audience more familiar with the notation later. And so you can think of the product as the trivial topological order. It corresponds to trivially graded part of the Z2 grading. And then the psi part, which is computational basis 1, corresponds to the non-trivial in the Z2 grading. So in this way, as always, we put qubits on edges. And then if we're talking about the honeycomb lattice, this is a ground state of toric code, where we can see an equal superposition of all such loops which are colored in blue. And there's another way to write down the ground state by using the Chrom-Sylvania duality. Suppose we have on the right-hand side initially a product state, then you add some ancilla on the plaquette, which is put in the plus state, and you act control plaquette operator, which is a product of control X. You can see it here. Control X on the 6 edges, where control is on the plaquette ancilla. And then after that, and we project it to the, we measure out the plus in the plus basis for the ancilla. Then you will get an equal superposition of the unit loops because half the chance, because the ancilla is in pluses, so half the chance you create a loop, the other half the chance you don't. So in this way, you create a ground state of a toric code. And what if this has already been mentioned by Kevin? So the important question is, what if you don't get the wanted plus result? It's OK. If you get minus, you just find out those measurements, and then pair them up using a string of these. This is very similar. It's almost the same thing as error correction in surface code. So the Ising category is very similar. It's just that we're adding another layer of the grading. So as you can see, we start to do the hierarchical thing. So we will put the previous grading by trivializing them. Everything is in black color. So let's just forget about them and only think about this red grading, which is second grading. And one the side previously have black and blue, now they're all black. And this sigma, which is the new, now it's acculturated because we have 3 things. And the sigma is the new simple object in the Ising category. It corresponds to the non-trivial grading. And skip here. So again, you can write down the ground state of the Ising in a similar way where we start with not just product state. Now we start with the ground state of toric code. We act controlled plaquette. That's B operator is the one in string NAT model or 11-win model. And control is again acting on the plaquette ancilla. As before, half of the chance you create a loop, the other half of the chance you don't. And then you measure out the ancilla, just as before. So, and the ground state picture is very similar. Just visually, instead of having 0 here, the black part corresponds to a local part that they locally look like the same as the toric code. And then on top of that, you have non-trivial grading, the red cycles, the red circles. So this is the ground state of the double Ising. And again, the measurements can be corrected if you get unwanted measurement. So this is the circuit to create a plaquette. This can be done in constant depth, so let's not worry about it. So those are the 2 beginning examples for nilpotent theory. So in general, a nilpotent anyon theory has a hierarchical structure for its extension. So you're looking at what you're looking at is equation 4.1. This is the bulk theory, the dream field center. So in the structure is that you have trivial topological order, and you have the first layer, second layer. At the end, you have all the excitations in theory. And each anyon in the case level can have an inverse partner, which will be fused deterministically to go to a lower level. We'll use that to create the anyons. For example, previously, the toric code has just 1 layer in the hierarchy. And double Ising has 2 layers in the hierarchy. And this is a layer 3 thing. And suppose we want to create a long string of this. And typically, you get unwanted excitation in the middle. How to clean it up? So you create these pairs and fuse them up. And as I mentioned, this will go deterministically to a lower level in the hierarchy. And if you keep doing this, you get the vacuum, so clean up all the unwanted excitation. Then you get a long string operator in constant depth. Again, this was believed to be like log or linear before. OK, so another main result is that for solvable anyons, you can prepare it in infinite depths using this adaptive circuit. It's just the only difference is that instead of do another go to the second layer directly. Now you need to gauge the area which is in between of the two excitations you want to create. And sorry, I was saying like condensing the area. And then keep condensing it until you get in this area, clean everything up. But this area is in trivial topological order. You want to repair this area by regauging it back. Then eventually you successfully make a long string operation. OK, so that's everything. And here's a summary. We extend the idea of preparing velocity via gauging to prepare all solvable anyons in constant depths. Condensing and regauging will prepare long string operators in constant depths. We also worked out examples in the paper, double S in double S3 and Tambara Yamagami. And we conjecture this construction captures all 2D phases that can be created exactly by AFDLU. Those are the references. And importantly, last year, Continuum has this paper that they create double D4 experimentally. So there's technically, there shouldn't be any advantage to realize our work. So that's everything.
OK, thanks. OK, so we're out of time, so I think we're going to have to save questions for this